All right. Hello, IT201 classes. Here we are in this week where we just went over the live lecture with dealing with user input, mouse clicks, how to determine where the mouse location is on the screen space versus world space, and then kind of projecting into the world, into this virtual world at a kind of a predetermined distance, and learning about prefabs and making more interesting objects to spawn. This is the first online video for this week. It's going to cover 2 more scripts dealing with this type of ray casting, figuring out the difference between screen space and world space. And then I'm going to do a separate video on how to do a test build, how to build to WebGL, how to zip everything up, and how to get it onto itch.io. So here's where we left off in class. We had this one file script called screen to world point, and we had some nicer prefabs. So as I click, you see, and if I hold down right mouse click for like auto quick spawn, let me click over to prefabs. These are these fancy objects that we had created. Each class we did a different one. All right, so that's script 1. I'm going to stop play here. And now these are the 2 other scripts I have to cover to wrap up user input for this Sprint 1 project. So I'm going to click on this script. I'm going to double click on it and open it. And I'm going to go through it line by line so that you can write it yourself. So the only difference is the class name slightly different. Click position manager. Second script, screen point to ray, where the other one was screen to world point. We're going to use a different function called screen point to ray. All right. So we have this public variable. We'll go over it later. You can ignore it. This whole thing lives in an update loop, and then the whole thing again just lives in a big if statement. All right, this if statement. So again, this update loop just running as quickly as it can. All it's doing is running this if statement. All this if statement is doing is checking if there's user input. In this situation for right now, again, we deal with a click, a button down, which is only true when you first click. So basically a left click. That's because I'm putting a 0 in here. We're testing for the first element of the array, which is left click. Here we're testing for when you're holding the button down, but we're holding checking the second button or the right mouse button. So a left click or basically a right drag. If any of those or any one can be true, we go in. So I went over this stuff in class. This is basically just creating a vector, which again, this is a local vector. We can just as easily make it global. And for your scripts, you can just get in the habit of popping that up there and making it global. But this is different. So here we are, method 2 down here. So again, I'm using comments to kind of label stuff, give you directions, write out pseudocode. In this method 2, we're going to do a ray cast using colliders. So ray casting is very similar to drawing out a line, a vector. We went over a vector in X, Y, and Z. A vector can also be used in many different ways. It can also be used as a position in world space. It can be used as a direction. And in this case, we're going to be using it as a direction. So again, we're going to reference our main camera, camera.main. We can only have one camera in the scene, dot screen point to ray. So this is a different function than the other one. And this one, as it reads, as the description says, it returns a ray going from the camera through a screen point, a point on the screen. So which is the actual point we're going to use? Well, we're going to use the mouse position. So in this method, in its parentheses, it's whatever its input is, we're going to place in input.mouse position. We're going to call the input class, find the mouse position within it. That's going to return a coordinate position. It will be a vector 3, but remember the third position Z is 0 because we're dealing with screen space. We're just dealing with the X and Y. As you saw, we kind of moved the mouse around in my demo app, and it was reading in the X and Y position of the mouse. So that gets fed into the screen point array, which creates a ray from the camera through a screen point. So basically, wherever the mouse is on the screen, we're going to shoot a ray out. We're going to shoot out a vector out through the mouse, out into infinity, into our world, and we're going to see what we're going to hit. So it's like shooting out a laser blast or shooting a gun, and we're seeing what that bullet, what that laser is going to hit. And we're shooting it through the camera, but we're angling it through where the mouse is. So that's why when the mouse is kind of hovering over an object, we're able to hit it and see what it is that we're hitting. So this function, this screen point array, is reading in the mouse input, and it returns, if we look at what its output is, it returns a ray. So we have to create a variable of type ray and name it something. In this case, we just call it lowercase ray. But this is another data structure. So we learned about the standard ones, like booleans, integers, floats, strings. We learned about more Unity-specific ones like vector3s, game object. Here we're learning about array, which is basically like a special vector, and it's used in the physics engine. And later on, we'll use physics to make fun interactions with these 3D models. But right now, we're using physics to actually figure out what we're clicking on. We're going to be using rays and colliders. The ray is like the active part, shooting this ray out through the camera, angled through the mouse position. And then we need these kind of passive elements, these colliders, these physics colliders on our objects to read in that it's being hit. It's the target point. So now we have a new variable called ray. Up here, we actually do have one final variable, but we'll talk about that later, or I should say a data structure class. So, this is actually a related variable, but different. It's called a raycast hit. So you need a ray. You need to shoot out into the world. It needs to hit some type of collider, which is our interactable objects with colliders on them. And the information that gets fed back, if it does hit something, if the user is clicking on something that's interactable, we get back what's called this raycast hit. So we just have to create the variable. We have to declare it. We do not have to assign it. It's going to be assigned in this function down here. So we declare array, which is kind of like a physics vector3. It gets assigned from this method called screenPointArray, which is feeding in from the mouse input through the camera. And then we create a raycast hit, but we don't assign it. It'll get automatically populated when we click on a collider in our world. We just have to declare it, and we just call it hit. So we have a data structure of type ray called lowercase ray. We have a data structure of type raycast hit, which is called lowercase hit, and it's not assigned. And then we do a check. This if statement, is only going to be run when we feed in, we test for a user input and that is successful, it's true. So like 60 times a second, we're checking, is there user input? If so, we create a few variables and we do a check. Did that user input, wherever that user was hanging their mouse around the screen and they clicked, and we shot a ray out into this virtual world, did that ray hit anything? So if, now we're using the physics system, we're using the physics library, physics.raycast. This is a method called raycast. And as you see in this method call, you see there's up to like 15 of these because it's such a popular or so useful, multi-useful method. But this one, we just feed in array. We feed in a raycast hit, which will be given out our information if there's a hit, and it will return a bool. So this method's a little interesting. If you notice, it says out. So the name is raycast. It lives within the physics library. We're going to feed in array. we're actually feeding in or connecting a reference saying this is the raycast hit, which will also be updated. That's what that out means. It'll actually, information will be sent out to that raycast hit, besides of the standard output, which is on the left, which is a bool. So this out term right here is new, this keyword. But anyway, raycast, it returns a bool, true or false. That's why it's in an if statement. So either wherever the user has clicked, there's something that had a collider on it. True, we do some stuff. There's no collider. False, we just don't execute this code and we continue on, which there's nothing else except a debug statement showing us where they clicked. This is another modified section of code, which we'll get to in a second. So we feed in this ray, which is angled through our camera, through our mouse, out into the world. We connect it to this other data structure, raycast hit, which gets populated with all of great information if we hit something, and then it sends true if we did hit something. Then we go into here and execute this code. So what's this code doing? Well, we take the raycast hit variable, which contains a lot of pieces of information. One of them, so hit dot, the dot operator, we use one of its member data structures, which happens to be called a point. And it's a point in the world space where the ray hit a collider, where the ray was shot through the mouse location, through the camera, out into the virtual world, and there was some object out there that had a collider on it. Where was that world space? That X, Y, and Z position, which we're going to call a point in this scenario, where was this collider? Where in the virtual world was this object that we clicked on? That's the X, Y, and Z, this point, which happens to be a point in world space, which is a vector 3 in X, Y, Z. So we feed it into our click position. This you should be familiar with. We were doing this in the previous script. And it's a vector 3. So now we know the location of what we're clicking on in our virtual world. So we have that location. Then we can create a game object and create a primitive sphere, connect it to this reference, this data object, and then update its position to the click position. Or you can do something, the next fancier situation, where we start instantiating prefabs. This is from the script from class. But this one is just using the kind of simpler method. Just create a primitive. Remember, this is an enumeration, a predefined list. So there's sphere, cylinder, cube, what have you. Create whatever you want, just get a reference to it. So we have to create a variable called game object and name it so that we can use the name to set its position. What's its position? Its click position, which is hit point. All right. So what does this script look like in action? So let's pop back over. We have the script turned on. You can ignore this variable. This is our next step in it. Just notice that it's set to nothing. We don't care about it. Notice in this situation that I have just a sphere that has a collider on it. And if I click play, I'm clicking, let me click my console, and this should be cleared out. There's the debug of -1. So this is why we put that negative vector 1, -1, -1, -1, because this is like gets printed out when nothing happens. And this is, we know that nothing happened because that number can't actually exist. So, but if I click on this sphere, which had a collider on it, let me just zoom up on here, you can see it a little bit better. It's actually spawning the spheres on it. And I could keep going until it just hits the camera. So, we did find a collider. So the only collider in this whole world, and if I click all over the place, I'm just getting -1, -1, -1. Which, let me jump back real quick. Remember, by default, we set it to -1. And that we have this debug log, so no matter what, even if nothing gets hit, we print out there at the bottom. which is what's happening. And then all of a sudden, this one object is hit. And it keeps building out this chain of spheres until it just covers the camera, and we can't go anymore because it's just right in our face. So, we did find something. We shot the point out through the mouse position, through the camera, and we checked, and we did hit a collider. And when that collider was hit, we sent that information back, and we used it to spawn a sphere and then place its position at that location. Which means when I click here, it reads where I'm clicking on that collider, which is on the outer part of the sphere toward the camera, because that's where I'm clicking on, because the collider is encapsulated. So if I click on the sphere, the collider is this whole volume of sphere. So as I click, it's finding that outer point of the collider, which is why these spheres keep getting populated closer and closer to the camera. Great. So I'm going to turn on this ground plane. Just looks like this. In fact, I'm going to turn it off. You can do it yourself. Go to Game Object 3D. Just click a plane. Just know that you get that random bit of information. Just reset the position. And I'm going to turn this sphere off. All we have is this ground plane sitting at world space 000, and it's got a collider on it. So if I click play, and notice I'm populating spheres on the collider. And if I click around it, nothing's being populated. You don't see stuff going in my hierarchy, and we're getting -1, -1, -1. So notice if I click on a sphere, though, on the plane, the sphere that we're creating, those spheres that we're creating, those Unity native default spheres, do have colliders on them, which is why every time we're spawning one, it's like a new collider, a new area, a new volume that we could potentially click on through our script. And that's why, as you see, I can click on different parts of my plane, and I'm growing these like sphere structures out toward the camera. Cool. So you can, I guess, one type of painting or growth program or modeling program or something. Sure, I'm sure you can find something interesting to think of to do with this. And as I look around, you see that I'm kind of growing lines of spheres from the points, original points on the plane that I'm clicking on. All right. So, what if I don't want to have all these objects growing out at me? Well, since I did introduce you to prefabs, a little workaround might be to spawn objects that don't have a collider. You can either turn the collider off, or you could just remove the component altogether. I'm just going to undo that because just leave that sphere there with the collider on. Just leave it as default. So yes, since I did introduce you to prefabs, some of you might think to create prefabs full of geometry with the colliders turned off. Okay, but let me show you or introduce you to physics layers. So I am going to comment out this section of the code, and I'm going to open up our next section of code. So everything's still the same. We're still creating click position. We're still shooting a ray out through the mouse position, gathering that ray, creating a raycast hit. All of this done within an if statement only that's executed when there's user input. And then we do if physics.raycast actually shoot a ray out. And this is a little bit different. This one had two, just a ray and a raycast hit. This method call has a ray, a raycast hit, a float called max distance, and an integer called layer mask. Okay. So the max distance says before that ray was just going out into infinity in our virtual game world. Sometimes you don't want that, so it's not optimized. It doesn't make sense. Maybe on the objects you're spawning are very close. Maybe there's distant objects you don't want to hit. So anyway, we're saying 100F, a float of 100, which the units in Unity are in meters. So this says shoot the ray out for 100 meters to see if there's a collision with a collider. All right, that's helpful. We can optimize. It takes less time to run our code. That's great. What's really important here is this layer mask. So, a layer mask, another data structure that's from Unity. As I hover over it, so UniEngine.layerMask specifies layers to use in a physics.raycast. Great. It's public so that we can update it in our inspector, and I'm just calling it click mask. So, click mask here. First off, this layer mask, our object needs to have this layer for the actual ray to interact with it. And we're going to do the same thing. Let me actually copy this code here. So we're going to gather that location where the hit happens, and we're going to create the sphere. So the only real difference here is that, yes, our array is limited on how distant it's going out, but it's going out 100 meters. This is far beyond. Our camera, I think, is like 10 meters from the plane. Not a big deal. Click mask is the big deal. So let me pop back over. Let me click on the object that's got my manager, my script on it. Now notice click mask here. If I open this, we have a bunch of layers. Where are these coming from? So up here, every game object has access to tags, and I kind of talked about it briefly. The main camera, like some people's cameras didn't have this tag, but now we're looking at these layers. So yes, you can add more layers, but we are just using the layers right here. Let me add a layer. I actually think, yes, I did. So I did create a custom named layer. So let me go back to my click detector. There you have these layers called everything's on default, which means all these physics layers interact with each other. Let me very quickly, you don't need to go into here, but project settings physics. This is behind the scenes of the physics engine. There's a lot of stuff that you can mess with, but normally you don't. This just says how the layers, you can put stuff on different layers if you don't want them all interacting with each other. This says that all these layers are currently interacting, so you can turn them on and off, and this makes like a custom physics solution for your game, your app. But just know that what these layers are working on behind the scenes, and we are going to actually create custom layers. So I can say add layer, and these user-defined layers, here I just called it ground click. So you can do that as well. And click on the actual plane, this ground, and we are going to call it ground click. Okay? So this sphere here, notice that there's no layer on it. In fact, I'm just going to move it up just a little bit so that when I have a different area I can click on, and I'm going to leave the layer alone. All I did was go on the ground plane right here and change the layer to ground click. So I'm just going to check my script is saved. I think that's good. I'm going to go back to my click manager script. In our click mask, I'm going to keep nothing for right now. Let me just see what happens. Okay, so nothing is interactable. And let me just turn on ground click. And now we can spawn objects on the ground. Awesome. So just to make, I'm going to create one more layer just to show you the difference here. I'm going to call this one sphere. So you have two custom named layers. They're not custom as far as attributes or anything. They just are new layers that have names on them. So our ground plane, I'm call ground click. This sphere floating up here, I'm going to call layer sphere. Okay. Our click detector right now is click mask nothing. So when I click, no matter where in the scene I'm clicking, actually let me just click on the console real quick. Notice how we're still getting that -1, -1, -1, that debug statement. And anything I click on we're not actually spawning. The if statement doesn't actually happen. So if I switch the click mask to sphere, notice how the plane still doesn't respond, doesn't create our raycast. It does not return true. But if I click on that sphere up there, it does return true. Actually, what's interesting is I'm spawning spheres, and they're still spawning as you see them, and they're only able to be spawned on that one sphere. These other spheres are being created. They do have colliders, but they have layer default. So the only good sphere is this first one. Let me just move it up a little bit because now I have this like cluster of spheres here. And I'll keep clicking and notice that I'm creating more and more spheres, but they're all clustering on that one sphere. Again, because these new spheres or colliders are no good. They don't have the right layer mask. So if I move to the click detector and switch it to ground click, now we can spawn spheres all over this ground. And notice how I'm not spawning any on these, on the spheres up here. But I'm spawning them on the ground plane. And most importantly, I'm only drawing or painting these spheres on this ground plane. And they're not, these new spheres that are being added are not creating new like collision points, new raycast spawning spheres closer to the camera. All right. So that is these layer masks. I'm going to click off it just to clean up the scene. And again, I just created 2 custom named layer masks. And I just wanted to show you that we can filter with this raycast method. We now can say which of these physics layers should we be reading colliders in from. That was the second script. And I'm going to turn that off. And now we have our last script. So I'm going to turn off this plane. I'm going to turn off this sphere. And I'm going to click play. And anywhere I click, even off to the farthest horizon, in fact, I'm going to turn the plane on. And notice that where I'm spawning spheres has nothing in relation to that actual little ground plane I created. It's actually looking out into infinity, into the whole entire ground plane, and it doesn't need me to create it. In fact, even if I turn my camera, I'm just going to rotate it off into another direction, I can still keep painting. Alright, so this is the last script we're going to talk about, and this will wrap up the lecture. So, I'm going to click back on click detector. It's the third script. There's a new one called plane raycast. Alright, I'm going to click over here. It starts off the same. Yes, the name is a little different because it's our third script called, we're using a different function now, different method called plane raycast. You can notice here that we have a private variable up here called GameObject primitive. I think all I did was, I got tired of constantly spawning primitive down here, so I just showed you that instead of having everything local, you can start to pull stuff up into being global. So I just have to create this GameObject data structure once called primitive. It's not assigned, and I only assign it down here. And when we create a primitive, in this case a type sphere, and then change its location to wherever we're getting our collision point, and then we just keep that one data structure and keep changing its reference, and then we know the data structure so we can change its position, and then we kind of release that reference. We forget about it when we create another one and connect to that one. So based on that, I can talk about, notice that it's a private variable, and notice it's not showing up here. And this is the next step where we don't have to make everything public. And we'll talk about the next stage where we can use something called serialized field, which means that stuff can be kept private, but we can show it in the inspector. So only the developer kind of has public access to variables. Other methods cannot mess around with another script's variables. But I don't think we're getting it to this week. So let's move on in the script. So again, we have our update function. All it is an if statement. It's checking for user input. We're creating that vector3, that click position. And then this is new. Method 3, raycast using a plane. So here's a new data structure. It's of type UniEngine. It's called a plane. It's very similar to GameObject 3D plane. And it's a very similar situation where we're spawning primitives primitive types down here. In fact, if I just remove this sphere here, dot, there is a plane also. But the difference between a primitive type plane and this type of plane is this is like a mathematical, infinitely large plane. It's not of a graphical, a visual nature. So you're not going to see it. And it's much lighter weight. It's just this infinitely large mathematical plane that we're going to use as our collision plane to click on. So, plane, which is a data structure of type plane, which is available to you from Unity. So, and as you can say, it's a representation of a plane in 3D space, just not 3D geometry. And we're going to call it lowercase plane. And we're set it equal to a new plane, and then we have to put some input data into this method call. So remember, new means it's calling this constructor method. So this plane class is kind of like when we're creating vectors, and we have to say new vector. It's because it's a more complicated data structure. It has several ways it can be constructed, and we have to be more specific and say, oh, just create an integer instead of equal to this. Well, it's always going to be some type of integer. That's not always the case with these more complicated data structures. So this plane constructor method, as you can see, there's 3 overloads. There's others methods. This one is just reading in a vector3 and a float. Okay, so we have vector3, the normal, so the direction that the plane should be facing. Just know that a normal in 3D geometry, it's let me actually create a plane or just turn this one on. It's whatever's perpendicular to where it's being rendered. So this plane that sits on the ground, it's like our horizon. Notice how the gizmo, I'm going to use this green arrow, this up arrow, as a representation of what the normal is. So the normal is the angle that is perpendicular to this polygon, to this face, to this piece of geometry. So this geometry is flat. You look down on it and you can see it. The normal on it is pointed up. So based on that little piece of information, when we're constructing these mathematical planes, we have to know what its direction, its normal is going to be, so that it knows how to render it. So in this case, we're just going to be creating a plane that sits on the ground plane, and it's pointing up. The normal is pointing up. So that's the first input piece, and then the second input piece is this float. It's basically where it's being positioned. So how high up is it on the Y? We want it to sit at 0.0. So we're basically going to create this infinite mathematical plane that's sitting on the ground, pointing up so that we can see it. So if I flip down, notice the underside of it, we cannot see it because these planes are only oriented in one direction. And it's going to be sitting at y equals 0. So that's what these methods mean. Okay, we have this plane created. Now what's next? Okay, we're going to grab our main camera. We're going to do this screen point to ray, which we used in the last equation. We're going to put in our mouse position. We're going to shoot a ray out through the screen, through the mouse position, see what we hit. Put it into a ray. All right, so now we're using this plane.raycast. All right, this is a little different now. So we were using physics.raycast before. Now we're actually using a raycast function that's part of this plane data structure. We're going to put in a ray, and in this raycast, it feeds in a ray, a vector direction, and it feeds out the distance, which is just a float. So the distance to the plane. So if we make a collision, if we click on a collider, or if we click on the plane in this situation, we put in the distance to the plane, and that's our click position. All right. So the ray, the actual physics ray, we're going to get a point that's the actual distance to the plane. And we're going to put that as our x, y, and z. And then we're going to create the primitive. So as I click play, notice that I'm clicking spheres, and let me turn off this one plane because I might be confusing the situation. So I can now draw spheres on this entire plane. All right, which is basically the out to infinity. So since this plane goes out to infinity, we have to know how far it is that we're hitting this plane. That's why we're using a little different now. We're using this distance to plane. So how far out were we clicking on this infinite plane? And that's how we get this ray, this position. It's through this plane.raycast. And then again, we just create the primitive, create the sphere. So let me unclick play. So notice that the plane I have rendered, if I rotate it 90 degrees, wrong rotation, I want to do it toward the camera. Say I want a plane out like this, directed toward the camera. And let me finish the rotation here. -90. Okay. If we want to have an infinite plane, kind of like this, that we want to click on, notice that the normal, the perpendicular angle to the face of it is not up and down anymore. It's blue, forward, backward. So let me just turn off that plane. Let me show you that instead of vector up, let's try vector forward, which from our forward and backward deals with z. So we have left, right, up, down, forward, backward. So if I hover over forward, it's shorthand for writing 0, 0, 1, or the z direction, or the blue arrow that I just showed you. So with that, I click play, and I'm painting or drawing spheres on this plane, this mathematical infinitely large plane that is at world space 0 from the camera. Remember, the camera is like 10 units off over here, -10. And it happens to be painting at world space 0 because we're creating the plane at world space 0, but we kind of flipped it. Instead of it being flat and sitting on the ground, it's now rotated and it's up sideways and facing the camera. So with this, we actually have our painting mechanism. So we can actually start painting spheres or whatever objects in front of the camera. Cool. So that was the for this week anyway, our 3 main scripts, and now we're good with user input. And next week we can do user interfaces, and we can actually finish this Sprint 1 project. And this part of the knowledge, this input and screen position, the world position, is complete. So I'm going to create one more video for this week, and that's basically how to do the WebGL build, how to get up on itch.io.